In the next two sections, I will show you a simple example of the use of multi-threading. This example will show you how to start 3 threads, and you will see the effect of threading. In the first section, I will do a code walkthrough. At each step, I'll show you the registers involved, the C code lines, and the assembly code for each step. In the next section, I'll go through the compiling and running of the code in the debugger. I have already shown you some of the macros that allow you to program the 34K in C. Just a reminder, these are located in include MIPS mt.h. The first thing the code needs to do is to put the processor into a mode where we can use the CP0 registers to configure the threads we want to run. The MVP control register has 2 fields, VPC and EVP. Setting the VPC field will allow us to write registers that are not normally writable on a single core MIPS processor. Clearing EVP disables all multiprocessing, so we can configure all the threads. The MIPS32 get MVP control macro reads the MVP control register. I clear the EVP bit using the MVP control EVP pound define, and set the VPC bit using the MVP control VPC pound defined. Then I write this back using the MIPS32 set MVP control macro. Here is the assembly code. Assuming the thread we are executing on is thread 0, I now want to configure the target TC so I can configure thread 1. To do this, I will use the target TC field in the VPE control register. Once I do this, the MTTR move to thread register instructions and the MFTR move from thread register instructions will be directed to thread 1. This is simple to do in C using the MIPS32 MT set target macro. Here is the assembly code. I want to make sure thread 1 is halted before I configure it. To do that, I need to set the halt field in its TC halt register. In C, I can use the MIPS32 MT set halt macro and the TC halt H pound define. Here is the assembly code. Now I want to bind thread 1 to VPE0. I will do this using its TC bind register. To do that, I'll use the MIPS32 MT set bind macro. This will write the register, and the TC bind cur VPE shift and the TC bind cur TC shift pound defines will place the values for the VPE and the TC in their appropriate fields. Here is the assembly code. I now set up the stack pointer and global pointer of the thread. I have previously allocated space for the thread stack and set the variable TC1 stack top to the last word entry in the stack, since the stack grows down. I use the MIPS32 MT set SP macro to write the stack pointer to the stack register. Here is the assembly code. The global pointer is used to reference the global variables in the small data areas. These variables are shared by all threads. To set the global pointer, I will use an external variable set by the linker called _GP and the MIPS32 MT set GP macro. Here is the assembly code. Notice that in the assembly code, I can just copy the GP register to the target thread. I now need to tell the CPU where to start fetching instructions for this thread. I use the TC restart register to do this. The macro MIPS32MT set restart sets the starting address using the start TC1 function pointer, which points to the starting function for the thread. Here is the assembly code. Now that I have the thread configured, I can activate it and make it available for use with fork and yield instructions. The TC status register is used to do this. To activate the thread, the A field is set. This example does not use the fork instruction, but it will use the yield instruction at the end of execution. So we do need to set the dynamic enable thread allocation by setting the DA field. I use the MIPS32MT get status macro to get the current value, and the TC status A and the TC status DA #define to set the bits, and then the MIPS32MT set status macro to write the value to the register. Here is the assembly code. The last step in configuring the thread is to unhalt it. By doing this, the thread can be scheduled and instructions can be fetched once I enable multi-threading. Clearing the H bit in the TC halt register unhalts the thread. The MIPS32MT set halt macro with a 0 argument will clear the H bit in the TC halt register. Here is the assembly code. To set up thread 2, I just set the target TC to 2 and then set up the same as thread 1. The one thing that must be different for each thread is the stack, otherwise the stacks will get corrupted. You can use the same starting code address, since each thread will have its own stack and therefore will have its own context. However, this example will use a slightly different code for each thread, so we will also change the starting address. After I have initialized all threads, I need to enable threading on the VPE. I do this by setting the TE bit in the VPE control register. To do this, I use the MIPS32MT get MVP control macro to get the current value of the VPE control register. Then I use the VPE control TE #define to set the TE bit, and then the MIPS32MT set VPE control register to write the register back. Here is the assembly code. Last, finally, to enable multi-threading and start all enabled threads executing, I need to turn off configuration mode and enable virtual processing. These are set in the MVP control register. I use the MIPS32 get MVP control macro to read the register, and then the MVP control VPC #define to clear the VPC bit to turn off the configuration state, and the MVP EVP #define to set the EVP bit to enable virtual processing. Then write the register back using the MIPS32 set MVP control macro. Here is the assembly code. At this point, all threads will be scheduled and will start running code. I now want to put the current thread that executed the initialization code, thread 0, into the mix by calling the count function. Note, the code will never execute the return because all threads will be yielded, including thread 0. The rest of the code will be used to show multi-threading and how the threads behave when run from cache or straight out of RAM. To do this, there are two simple functions, each of which I will increment a counter in a global array. The first function, count, accesses the counter in the array using the cached address. The second function, encount, increments the counter in the same array but through an uncached address. What you will see is the threads that use the cache address to increment their counter will not stall, and these threads will execute more than the thread that is writing to the uncached address. This is because the threads using the cache address will be allowed to execute while the thread that uses the non-cached address stalls waiting for a load to complete. Fine-grained multi-threading allows other threads to execute while other threads are stalled. Normally, these stall cycles would be wasted on a non-threaded CPU. Each thread will use the yield command to terminate itself once terminal count has been reached. You will see that threads using the count function will terminate before the threads executing the endCount function because they have gotten to run while the endCount function was stalled. The example will use Navigator ICS and the MIPSIM Cycle Accurate Simulator. I'll set breakpoints and open a memory window to examine the counters. I'll switch between the threads to show each thread's context, and I'll show you how to set a breakpoint on a per thread basis. The project contains 3 files. The 1VPE3TC source code file contains all the source code. The 1VPE3TC34K.CFG file is the MIPSIM simulator configuration file, and the MIPS mem inf 34K config is the memory configuration file for the simulator. I'm now going to show you a demonstration of the code we just went through. We're in Navigator ICS. We're going to be using a Malta evaluation board with a 34K bit file in the FPGA. Start out by going to the workbench. We're going to create a new project. We're going to create an empty project to start out with. We're going to import the code that we were looking at. It's in the general area. We're going to import a file system. Browse to that file system. Select the files. And you can see the files in the project. I will change the properties of the project. We're going to go down to Build and Settings. Select the processor. The board is set up as little endian, so we're going to select little endian. And we're going to select the linker script. Now we're going to build. We can see we built without any errors. Create a debug dialog. It filled in the project and the application. Going into the debugger, we're going to be debugging with a probe. Let's look for that probe. We found one. We're going to choose a 34K configuration. These are CAN configurations. And we're going to hit debug. This takes a while because it's on a FPGA, fairly slow processor. Okay, so now we can see a couple of things. We're in, let's open some of these up so you can see a little bit more about what's going on. You can see there's one thread running and we're in the main function. We can see the local variables for that thread. We can see where in the C file we are stopped. We're stopped at the first line in main. And on this side I've got assembly view up so you can actually see which assembly code we're going to about to be executing. So one of the things we're going to do is we're going to add a global variable that we want to be following along, and that's the counters. So if we look at this, we can see that this is an array of counters. And we're also going to set some breakpoints. I'm going to set a breakpoint at the point that each one of the threads has finished its loop. So we're going to, this is the count that the thread that's going to be counting in uncached space is going to use. And here's the count function that the thread that's going to be counting in cache space is going to use. So we've set those breakpoints and we continue. And we can see we've hit the breakpoint. We can see that this thread here is suspended. Breakpoint hit. We'll select its context. And we can see that actually two of the threads have hit their terminal count, 100. In this window you can see that we actually have 3 threads running. So this thread here is suspended. You can take a look at its context. You can see that it's the thread that is counting in non-cache space, and it has a count value of 47. The other thread, we can expand it, and we can take a look at its context, and its context shows where it's at too. So from here we're going to actually continue. So that was one thread at the yield point. We should hit the other thread at its yield point. And we see that we're now in this thread's context. And we see it's at its yield point. Still see the counts at 100. We go back here. We can still see the count at 47. So we're going to continue one more time. This time we're going to see those 2 threads have actually yielded and exited. And this thread here is now had a time to count because the other threads were no longer in the system, and we have reached a terminal count. So at this point we'll stop the debugging. We'll clean up the terminated, and we can go back to the building view, and we could edit the program if we wanted to.